Next up, question 8 says, for each sequence, determine A if it has a limit, B if it's monotonic, and C if it's bounded. All right, now I apologize in advance. This is going to be a fairly long video. You can see there's a lot of different types of examples here. I just wanted you to have enough to go off of, so certainly feel free to just fast forward through this. Just use the video in any way that is helpful for you. But in any event, let's jump into the first example. We got the sequence whose nth term is n squared over n cubed plus 1. So here's the first couple terms. All right, so now for part A, it's asking us, does this thing have a limit? Well, first note that the numerator n squared will approach infinity, and the denominator n cubed plus 1 will also approach infinity. And so the question really is, who's going to win out? Who grows to infinity at a faster rate? And the higher exponent here for the n cubed means that it will grow to infinity faster. And so since that's in the denominator, that's going to carry the sequence to 0 in the limit. So to actually show that more precisely, we're going to go ahead and divide numerator and denominator by n squared. So that's going to give us 1 over n plus 1 over n squared. And notice here as n approaches infinity, this n approaches infinity, and 1 over n squared approaches 0, meaning this entire denominator approaches infinity, and so 1 over it will approach 0 as n approaches infinity. So this sequence converges to 0. All right. Is the sequence monotonic? Well, to answer that, first I'm just going to bring up a picture illustrating the sequence. So here's the corresponding function. F of x is x squared over x cubed plus 1. And then in red, you can see the terms of our sequence. And from this picture, okay, even though the blue curve has this interval where it's increasing and then it turns around, and then this interval where it's decreasing, so the blue curve, while it's not monotonic, it does appear that the red sequence, which is really what we're interested in, is monotonically decreasing. So how do we actually go about showing this? Well, first note that this first term, right, is to the left of this peak on the curve. But again, it is larger than this second term right here, right? This first term of our sequence is a half, then it goes to then it goes to 0.4 repeated, so on and so forth. So here's how we can do this. Let's show that the blue curve is decreasing for x greater than or equal to 2. Okay, that will imply that from 2 on, our red sequence will be decreasing. And since we already know we're decreasing from the first to the second term, that will allow us to conclude that the sequence, yes, is monotonically decreasing. Okay, so let's do that. Now, how do you show a function's decreasing? You can show that its derivative is negative, all right? So the idea here is to show that f of x, which is x squared over x cubed plus 1, is decreasing. And as I just noted, it's enough to just show that that's true for x is greater than or equal to 2. Okay, and we're going to do that by taking the derivative. So there's that derivative. Got to use the quotient rule, right? So we're going to have x cubed plus 1, so that's the low, times the derivative of 2x. That's the derivative of x squared, which is 2x. Minus high, that's x squared, times the derivative of the thing below, and that's going to be 3x squared, and then divide all of that by x cubed plus 1 squared, right? So low d high minus high d low all over the square of what's below. All right, now I cleaned up the top and factor out an x, so that's x times the quantity 2 minus x cubed all over x cubed plus 1 quantity squared. Now, when is that expression going to be negative? Well, since we're interested in the case when x is greater than or equal to 2, in particular, this x right here will be positive, and the square down below, that's also positive. So this entire expression will be negative when this factor, 2 minus x cubed, is negative, and that happens when x is strictly larger than the cube root of 2, which is about 1.26, which if we go back to our graph here, notice, right, the cube root of 2 is where this blue curve has this maximum. Okay, so going back, we are able then to conclude that if x is greater than or equal to 2, this expression will be negative, right? 2 is more than 1.26, so we are looking at a negative derivative on this interval. And so, yes, the sequence is monotonically decreasing. Okay, and then how about bounded? Well, yes, it is bounded. In fact, we can use 1/2, which is just the first term of the sequence, as an upper bound. Why? Well, because we are a non-negative sequence, right? All the terms live above the x-axis, and we're monotonically decreasing. So this very first term is an upper bound for the entire sequence. Okay, so this is a bounded sequence. All right, great. Moving on then to part 2. We got the sequence a sub n, which is the ratio of 3n minus 4 and 7n plus 5. Here's the first couple terms. All right, so for part A, it says, does this thing have a limit? Well, notice here the numerator, 3n minus 4, that's a linear function that's going to approach infinity. The denominator is also a linear function. It's going to approach infinity. But since they're both linear, the numerator and denominator, they're going to approach infinity at comparable rates. So there we're going to get a finite non-zero limit. And what is that limit? Well, we can do a similar maneuver as in the last example. I'm going to divide the top and bottom by n. So I get 3 minus 4 over n all over 7 plus 5 over n. 4 over n and 5 over n go to 0. And so this thing will converge to 3 minus 0 all over 7 plus 0, which is just 3/7. So this sequence converges to 3/7. All right, how about B? Is this thing monotonic? Well, again, real quick, I'll pull up a picture of the sequence. Here we're looking at the sequence for part 2, and corresponding function in red, the 3x minus 4 all over 7x plus 5. And this thing does appear to be monotonically increasing. Okay, so how do we go about showing that? Not just by relying on the picture. Well, we can do that by showing that this function has a positive derivative for x greater than or equal to 1. And so to compute the derivative, use the quotient rule again, right? Low d high minus high d low all over low squared. And this simplifies to 43 all over 7x plus 5 quantity squared. And that note is strictly greater than 0 for all x greater than or equal to 1 because the numerator and the denominator are positive. All right, so yes, this sequence is monotonically increasing. So it's a monotonic sequence. Is it a bounded sequence? And the answer there is yes. So we're leveling out. We're actually approaching what? Well, a limiting value of 3/7. And so here, if I draw this horizontal line at 3/7, and then here, this is minus 3/7, notice all the terms are trapped within this band, right? This finite band. And so from our definition of what it means to be bounded, this thing is bounded, right? The absolute value of all of our terms are less than or equal to 3/7 for all n greater than or equal to 1. All right, so we got a bounded monotonic convergent sequence. Okay, now let's turn to part 3. All right, so we're looking at the sequence. This is an alpha, Greek letter, alpha sub n, where alpha sub n is this difference of logarithms, so the natural log of n minus the natural log of n squared. All right, my first recommendation here is to rewrite this thing using log properties. So I'm going to first use what's called the power rule for logarithms. This 2 can come out in front, so this is the natural log of n minus 2 times the natural log of n. And that's just a negative of the natural log of n, because I have one of them here and I'm subtracting 2 of them here, so that's a negative natural log of n. Okay, it's a little nicer to work with. And so for part A, does this thing have a limit? Well, got to recall that the natural log function, it approaches infinity as we let its argument, in this case n, approach infinity. And so with this negative in front, that means that the negative natural log of n will approach negative infinity. All right, here's a graph, by the way, of that sequence. So the negative natural log of x in blue, and then you see the corresponding sequence terms in red. And although it kind of looks like this thing might level out, it never actually does level out. This thing will approach negative infinity. It approaches negative infinity at a rather slow rate, but nonetheless, it does approach negative infinity. All right, so this thing, since it's not approaching any single one value, this sequence is divergent. Okay, is it monotonic? Well, again, looking at the picture, it does look monotonically decreasing. How do we prove it? Well, again, we'll use the derivative. So take the derivative of the function negative natural log of x, which is not bad. F prime is just negative 1 over x, right? Because the derivative of log x is 1 over x. And this thing is negative for x greater than or equal to 1, certainly. And so, yes, this thing is monotonically decreasing. All right, cool. Is it bounded? Well, no, it's not bounded because alpha sub n, remember, approaches negative infinity, so I cannot capture all of the terms of the sequence in any finite band, right? If I keep zooming out, this thing is going to escape any finite band that I consider. So it's not bounded. All right, that's part 3. Let's press on, look at part 4. We got negative 2 raised to the nth power. First couple terms of negative 2, 4, negative 8, 16, so on and so forth. Here's a picture of that sequence. So we go from negative 2 to 4, negative 8, 16, negative 32, 64, so on and so forth. All right, so does this thing have a limit? No, it does not, right? Why? Well, because as we let n get larger and larger, 1, we have a sign alternation, and 2, the magnitude of the terms will become infinitely large. So this sequence does not approach any one specific value, and so it diverges. All right, is it monotonic? No, it is not monotonic. Why not? Well, really, the first 3 terms are enough to conclude it's not monotonic, because notice we increase from here to here, but then we decrease. And yes, we do other stuff, but those first 3 terms are enough to conclude that the sequence is not monotonic. Is it bounded? No, it is not bounded either. Why? Well, because, as I already noted, right, as we let n increase, the magnitude of the terms will become infinitely large. Okay, so if I keep zooming out, right, I'm going to see terms that are just growing in magnitude there, and there is no way to capture all those terms in a finite band. All right, very good. Let's press on then to part 5. We got b sub n is negative 1 to the n times n squared all over n squared plus 3. All right, so does this thing have a limit? Well, first, ignoring the sign alternator, the negative 1 to the n, let's just look at the n squared over n squared plus 3. Okay, notice the numerator and denominator here are both quadratic. And so as this argument shows, right, if I divide top and bottom by n squared, this is 1 over 1 plus 3 over n squared. Now as n approaches infinity, 3 over n squared will approach 0, so this expression will approach 1 over 1 plus 0, which is just 1. Okay, so now what's going on with b sub n? Well, as we just noted, n squared over n squared plus 3, that thing is going to get closer and closer to 1. But see, this negative 1 to the n is going to alternate our sign. So b sub n is going to be approaching values that alternate between things really close to positive 1 and really close to negative 1. Let's look at a picture. So here's 1, here's negative 1 in red, and you can see this, the terms of the sequence here in blue. So we start down here, then we jump up, and then we're just bouncing back and forth as we move to the right. And yes, the magnitude of the terms are all getting closer and closer to 1, but because of that sign alternation, okay, this thing is, the terms are not going to approach one specific value, so this limit does not exist, and so this sequence diverges. All right, Is this thing monotonic? No, it's not monotonic. Kind of like the last example, the first three terms are enough to see that, right? We increase there, but then we decrease, and so we're done. It's not monotonic. Is it bounded? Well, here the answer there is yes. This is bounded, right? In this case, I can capture all the terms in the band from -1 to 1, as you can see in this picture here. In this red band, all my terms in blue will be captured within that band, so it is a bounded sequence. Cool. All right, so then let's look at this next one, part 6. And so here we have the sequence C sub n is e to the -n times the sine of 2n. All right, so does this thing have a limit? It does. Okay, so this is going to be a squeeze theorem argument. All right, so first note that the sine on its own, the sine of 2n, this is always between -1 and 1, right, for all n greater than or equal to 1. So then if I multiply each one of these expressions by e to the -n, right, that implies that negative e to the -n is less than or equal to e to the -n times the sine of 2n, which is then less than or equal to positive e to the -n. Okay, so now what happens to e to the -n as n becomes infinitely large? It approaches 0. And so this thing on the far left will approach 0. This thing on the far right is approaching 0. So our sequence, the e to the -n times the sine of 2n, it being squeezed between these two things both approaching 0, it will also have to approach 0. So this sequence converges to 0. Now I'm going to go ahead and show you a visual for that one. So here we see this e to the -x sine of 2x. Okay, so now in this little window, this green curve up here, this is e to the -x. And this is negative e to the -x. And you can see the curve in red, which is our e to the -x times the sine term. It's always, well, it's squeezed in between those two things. So this is a nice illustration of this inequality you see right here. Okay, and again, since with the green bounding curves approaching 0, our curve is also approaching 0, so of course then the corresponding sequence approaches 0. So we have a convergent sequence. Is it a monotonic sequence? The answer there is no. So here we decrease and then we increase. So those first three terms say no, it's not monotonic. Is it bounded? And the answer there is yes, it is bounded. Okay, you can see from the picture the magnitude, right, of our terms approaches 0. And as a bound there, we could take, say, 1/2 as a bound. I could even take, this first value if I wanted to. The 0.3345 is like a tighter bound, but taking, say, 1/2 is sufficient. So all of the terms in blue live between -1/2 and +1/2. So yes, we are looking at a bounded sequence. All right, very good. That's part 6. And then next up is part 7. As I said, this is a pretty long video. We got beta sub n, another Greek letter. 3 to the n plus 4 to the n, all divided by 3 to the n. Okay, here's my recommendation for the first part, A. Let's rewrite this. So if I divide 3 to the n by itself, that's a 1. And then 4 to the n over 3 to the n, that's really 4/3 to the nth power. Now what happens to this term as n becomes infinitely large? Well, since the base here is 4/3 and it's more than 1, as we argued in question 7, this thing is going to become infinitely large. So that says that this sequence beta sub n will approach infinity as we let n approach infinity, and so this is a divergent sequence. All right. Is it monotonic? Yes. Here's a picture, by the way. And as you can see here, this thing is just a nice exponential function, right? It's just, as we already noted, 1 plus 4/3 to the n. And since this base here is larger than 1, this is an increasing exponential function, so that is a monotonic function. Is the thing bounded? No. Well, why? Because our sequence is becoming infinitely large as we let n approach infinity, and so you cannot capture all the terms in some finite band. So, okay, so now for the very last one here, this is part 8. S sub n is equal to the sine of n all over 5n. Does this thing have a limit? Yes, it does. Let's check out why. This is another squeeze theorem argument. So the sine of n is between -1 and 1 for all n greater than or equal to 1. And so here, if I multiply each one of these by 1 over 5n, I get that the sine of n all over 5n is greater than or equal to -1 over 5n and less than or equal to positive 1 over 5n. And since 1 over 5n goes to 0 and the terms of our sequence are squeezed between these two things, right? -1 over 5n on the far left and positive 1 over 5n on the far right, and they're both going to 0, our sequence must also converge to 0. Let's pull up a picture of this last sequence. So there's the corresponding function. By the way, this is 1 over 5x, and this is -1 over 5x you see here in green, kind of like that previous example. And since these things in green are approaching 0, right, the curve in red, and so our terms of our sequence in blue will approach 0 as well. Okay, cool. So it converges. Is it monotonic? No. And notice here, so we decrease, 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 but then we start to increase there. And we're just getting that oscillation from the sine term. Okay, so it's not monotonic. Is it bounded? And the answer there is yes, it is bounded. In this case, just looking at the graph, I can see that since I know my terms here are sandwiched in between these green curves, and this top curve, or sorry, this first term here is an upper bound, this 0.1683, right? This thing can serve as a bound, but to make it a little bit less messy, I'll just take 0.2 and -0.2. So all the terms in blue, as I noted here, will live between -0.2 and positive 0.2. So yes, it is a bounded sequence. All right, so again, long video, but that gives you a lot of different examples to go off of, and it's a nice summary of all the key things we've looked at up to this point. All right, I will see you next time. Thanks.